This is lecture 3 from chapter 9 of chemical bonds. And so this section is going to talk about actual chemical bonds. We're going to focus mainly on the ionic and covalent bonds. I'm not going to talk really any more detail on metallic bonds. So ionic bonds, this is the chemical bond of electrostatic attraction between negative and positive ions. Okay, so what does that mean? It just is talking about the attraction between a negative and a positive ion. It works the same way as like what we saw with electricity. Positives and negatives are attracted to each other because they're opposites. And so this bond is going to occur because those negative and positive ions are going to be attracted to each other. So that's all we're looking at here. So ionic bonds are generally going to be created between a metal and a non-metal. And that is because if you remember from what we've been seeing when we make an ion, something like sodium is going to make positive ions because the things that are metals are going to tend to lose their electrons. And something like chlorine or fluorine, these guys are going to become negative ions because they're going to tend to gain electrons. So we generally are going to get an ionic bond between a metal and a non-metal. So pretty much all the ions we see are going to be between these two kinds of sets. Oh, and that's why. And what's kind of interesting about ionic bonds is they tend to create orderly geometric structures. So most of these ionic bonds are going to create crystals. So we've got cubes and diamond type shapes, very orderly structures because of the way that these positive and negative ions are attracted to each other. The thing is that ionic compounds are not composed of molecules, and this is because of the nature of this attraction. They are actually not physically bonded together. They are not actually stuck to each other in a permanent type of fashion. They are not super easily, but comparatively, compared to something like a metallic bond or a covalent bond, these are going to be easily pulled apart. Think about something like salt in water. So if we put salt into water, the salt dissolves. That's because the water molecules are able to come in and pull the sodium and the chlorine apart from each other. And so we don't say that we have salt molecules. We say that we have salt ions because these guys are going to be actually separate from each other, even though they're bound together in an ionic bond. So we take a look at one of these. So the best example of an ionic bond is salt, sodium chloride. So we know it as table salt. And what we can do, we saw these electron diagrams at the end of chapter 8, so we can use these to show electron transfer. So we can draw our little electron dot diagrams, sodium with its single electron, chlorine with its one missing electron, and then we can show that transfer, sodium becoming positive, chlorine becoming negative, and you can see they're not bonded together. There's a little bit of a space, but this is the new compound. And you can see here is the structure. So they line up in order. So we've got chlorine, sodium, chlorine, sodium, chlorine. You can see that they show order themselves into this cube shape for sodium chloride. And actually, if you look at sodium chloride under a microscope, they are little tiny cubes. So if you ever get a chance to look at table salt under like a hand microscope or under a hand lens, you will notice that they are actually tiny little cubes. So electron transfer rules. How does this work? So the atoms will gain or lose valence electrons to complete their octet, and they're going to create those positive or negative ions. So if you have one or two of those negative, or I'm sorry, one or two electrons in your outermost shell, so you're just hanging out with one or maybe two, that means that you're going to lose those. If you've got all of your electrons, give me 1 second, except you're missing, say, one, then you're going to gain in order to make yourself into a negative ion. So we've got that. The next thing is, how do we make one of these ionic compounds? So the thing is that there has to be a balance between the number of electrons lost and gained by the atoms in a reaction making an ionic compound. So the one that we just saw, sodium and chlorine, this guy lost one, this one gained one. These are balanced, right? It's 1 to 1. But not all of the compounds are going to work that way. So we saw sodium chlorine, but here, for example, is another one, calcium fluoride. So calcium, if we see calcium, if we set it up with its electrons, calcium has actually got 2 extra electrons sitting out here. And so it's going to lose 2 electrons to become +2. So it's going to get rid of these. And now you've got fluorine. Fluorine is like chlorine, and it's got 7. I know, it's incredibly awesome to watch me draw electrons. If it makes you feel better, you would have been watching me draw them in class too. So it's going to pick up an electron right here. So it's going to be negative. So what you can see is that this isn't balanced. So we've got a +2 here for calcium, and we've got a negative, just -1 for fluorine. And so what we're going to do to make this a compound is that this travels right here to make the formula, because we're going to need 2 of these guys to balance out the number of electrons. Because we have +2, we're going to need 2 negatives in order to balance out the number of charges. And so we get 1 calcium to 2 fluorines. So we'd actually need a second fluorine down here. That is a negative. Now we've got 2 negative charges to 1 + 2 positive charge. Now we've got an ionic compound that's balanced, and this is going to be our new ionic compound. So, oh, look at that. There they've drawn out what I was just talking about. So when you're creating those ionic compounds, those charges have to balance. So you just watched me draw this, so there it is, nicely drawn out. What do these guys look like when they make their compounds? The A families are going to make white crystalline solids. So anything that's made out of sodium or potassium, they are just going to be white crystalline solids. It's very difficult to actually tell them apart from each other unless you use them in some sort of reaction. They all dissolve in water to form colorless solutions, and they all conduct electricity as an ionic solution. So if you have them dissolved in water, you can use that to conduct electricity. This is actually why it is more dangerous for us to stand in salt water than it is for us to stand in fresh water if there is an electric current. The A families, except for this guy right here, 4, will form ions, as will the transition metals. Some of them will be more common to do it. So if we take a look at the elements, families 1 and 2 are going to definitely make ions. Families 6 and 7 definitely make ions. Um, Family 4, these guys will not make ions, and we'll see why here in a little while. 3 and 5, they can make ions and sometimes will, but more commonly, these guys, 3 and 5, are going to participate in the same type of bond as we see here with number 4. So, all right. So there you can see 3 and 5 have a lower tendency to make ions. And then again, all the transition metals, all of those B families are going to make ions. So here you can see some of the different charges that we get from ions. Now again, the periodic table will tell you most of these because it's based on their family number. So you can see there, here these are all in family 1, group 1. These are all in group 2. There's one from group 3, aluminum. There's one from group 5. So these guys are going to be going across. Oh, wait, no. Yeah, 5. That's 6. And then this is group 7. Sorry, I was counting the wrong direction. Over here, these just show you some of the ions for the transition elements, and you can see why I don't ask you to know any of those guys. If you need to know a charge for one of these for an element, I will tell it to you. I'm not going to ask you to remember the charges for some of these, obviously, because yeah, they're variable. You can see we've got a large variation from 1 to 7 depending on what the element is. There are also ions called polyatomic ions, poly for more than 1. So what these are charged groups of atoms acting as a single unit. So they act as one atom, but they are actually multiple atoms. So you can see here we've got borate, that's boron with 3 oxygens attached. So this is actually 4 atoms, but they act as one. And what they do is they act as an ion. So something like borate is a -3 ion. So these guys, I'm not going to ask you to memorize. You will have access to this table, or I will tell you the charge for a polyatomic ion if you need it. But I want you to be aware that these do exist. Some of these you may have heard of. So you've got ammonium, we've got carbonate. That's one that you've probably heard of. That's in some things. We've got cyanide, nitrate, nitrite, hydroxide, phosphate, sulfate. Those are more common ones. Permanganate, if you've ever done any chemistry, you may have come across that one. But some of these other ones that I named off are things that are ions that are in compounds that you use. So you've probably heard of some of these before. All right, I'm going to stop there and I will pick up with covalent bonds in our next lecture.